So thank you very much. Thank you for the introduction. I'd like to thank the organizer for initiating this trimester in Bonn, and which is very profitable. And also thank you for giving me the opportunity to speak here today. So actually the title is a simplification of actually smooth non-commutative U1 principal bundles. I just call them U1 bundles because it's much shorter. So I'm going to start by discussing Functorial Rieffel deformations. So the present work is currently in progress with Ralph Meyer. The Rieffel deformations, it's a way to start from an action of a group G on on an algebra A and to construct a deformed algebra A phi. The important point in Rieffel deformations is that they preserve the topological structure that we are interested in. In our case, it will be mostly Fréchet algebras. The motivations for our joint work are two recent papers. So first one by Lechner and Waltman 3 years ago, in which they consider an action of the group Rn on some locally convex vector spaces. They use oscillatory integrals and they deform both algebras, deform simultaneously, algebras and modules. Another source of motivation is a recent paper by Simon, Gianni, and Walter last year, in which they consider actions of Tn, and they make functorial deformations. That is, not only do they deform both algebras and modules, but they also preserve some morphism. But I come back to the definition of functorial deformations a bit later on. So our aims in this project is to combine somehow these two papers. So we would like to do functorial deformations, just like here. We would like to treat a more general class of group, namely locally compact abelian groups G, and would like to avoid as much as possible oscillatory integrals. We'll see how we can somehow bypass this problem. Further difference between the previous work is that we are going to be interested in cohomological aspects of our deformations, and I'm going to illustrate our results with the case of U1 bundles. Okay. So far, no. Okay, so this is what I'm going to do. Start with defining Functorial Rieffel deformations, then define this notion of U1 bundle that I mentioned in the beginning, how we can use our method to deform these U1 bundles, and if we have time, we'll discuss the different proofs. And yeah, please don't hesitate to ask questions during the talk. Yeah, that's always good. Okay, so Functorial Rieffel deformation. In this talk, we consider G a locally compact abelian Lie group. Our paper is actually written for general locally compact abelian groups, no Lie involved. But then you have to work with bonological spaces, and since we want to stick to Fréchet spaces, we'll stay safe and keep and use Lie groups. Then. So functorial deformations means that certain morphisms are preserved under the deformation. If you have a nice morphism of algebra between A and B, and that this belongs to the good category, then it is preserved once you've deformed. The question is, what sort of category are we going to use? So the category we're going to use is that of smooth tempered representation of G. We'll denote this way, but we won't see that symbol much. So smooth means what you expect since we are looking at Lie groups. It also has a meaning for more general locally compact abelian groups, but yeah, we won't discuss that. Tempered, I'm not going to define it right now, but I give a characterization in a second. And so the idea is if you have a G action on A here and a G action on B here, which is smooth and tempered, then, and if psi is equivalent, then it's going to be preserved. So, nice thing is we have a projective tensor product on these smooth tempered representations. So you take V1 with its representation of G, V2 with the representation of G. You have on Fréchet and actually on monological spaces this projective tensor product. You equipped it with the diagonal representation of G on, with diagonal representation of G on the tensor product. And what you get is, once again, a smooth tempered representation. So now I can state the characterization of temperedness. It's that if you do the tensor product of the Schwarz algebra with the vector space, and you make this tensor product over the Schwarz algebra, then you recover the algebra V. So this is a key property that we're going to use to define our deformations. Let me just discuss a bit the Schwarz algebra, which is here. So it's so for Lie groups, it has the meaning that you expect. For things that are just locally compact abelian, Brugha has defined it, and so it also has a meaning. We're going to use its with its convolution product structure. Let me just say that we can ask whether there are such example of such representation, and if you consider the Schwarz algebra itself and make the tensor product over the Schwarz algebra, and then the outcome is isomorphic to the Schwarz algebra. So we have at least one example of such smooth tempered representation. Ah, yeah. Yeah. Okay. Right. Further nice property of this smooth tempered representation is that they form a monoidal category. That is to say, we know how to form the tensor product of these. We have a unit, which is just the trivial representation, on C, and we also have an associativity property for this projective tensor product. Since we have a monoidal category, we have induced notions of algebras and modules. Okay, so algebras means that you have such a map which is in the category, okay? And modules is something very similar. So of course, if you consider, if your category is that of smooth tempered representation, the algebras in this sense are something which you can call G tempered algebras, so with an action of G which is tempered and which is compatible with the representation. That's what we've written here. Same thing for the modules. Okay, so now a summary, an announcement of what we want to do. We're going to use this structure of monoidal category to give a meaning to natural transformations that we can then study. So these natural transformations with associativity are going to define this map phi AA, which we're going to use to define the deformation of the product on the algebra A. You see, start from a G-tempered representation, from a G-tempered algebra A, and define a new product M phi on it. So, yes. So, what do I mean by natural transformation? So, it's a family of maps, just like that, such that whatever your choice of V and W in your category, this diagram commutes. So this is somewhat abstract. I'm going to make it concrete in the following proposition. The natural transformations from this kind of tensor product to the same tensor product are in bijection with the multiplier algebras of the Schwarz algebra, Schwarz algebra of G times G. So you see, we're not going to consider natural transformation of a single space, but rather two spaces, which is not so surprising, since what we want to do is really to deform the algebra structure. So I say natural transformation is the same as multipliers of the algebra of SG. Sorry? No. There is an of missing. The multiplier, the notion of multiplier that I use is here. Okay? Yes, yes. It's really for pairs of vector spaces, V1 and V2. Okay. So, what is there? Well, V1 and V, then it's going to be 0. Your morphism, you don't have that. No, but I mean, it's really, you've got something which is defined on all of the category, which corresponds to a multiplier of the Schwarz algebra. Yeah, for all V1 and V2. So here is the definition of our natural transformations. So we could start by specializing to the case when V1 and V2 are also equal to the W1, W2, which are just the Schwarz algebra. Okay, you're here. Then you can specialize what is the morphism that you take here. So you're going to take just a product with a fixed element, and this is going to be true for any fixed element. And now you look what are the properties satisfied by mu. This diagram here really means that you have that. Okay. So, starting from a natural transformation defined for all couples of vector spaces, I get a multiplier. Conversely, if I have a multiplier, so yeah, just a remark, this is purely formal, okay? This would work without even asking that we have smooth tempered representation. The other direction, however, requires strongly the fact that we have a smooth tempered representations. Okay. So starting from multiplier, we're going to go to natural transformations. What we do is that we use the isomorphism that Schwarz algebra. Put it like this. Okay. So the property that we are going to use, critical one, is that when you do the tensor product of this over the Schwarz algebra here, you end up with the vector space itself. Okay. So yeah, it's just yeah. So we define something at the level of the decomposed algebra as being the multiplier times the identity. And since mu is a multiplier, this is going to give us something which is well defined on this tensor product of the Schwarz algebra. And all these diagrams are going to commute. Okay. Yeah, that's a computation that one needs to do. And so the outcome is that starting from our multiplier mu, I managed to construct a natural transformation which is defined for all these pairs of vector spaces. And here something is really happening. It's because we've got natural natural transformation construction is somehow replacing the oscillatory integrals. Of course, the difficult point in explicit computation is to somehow realize this identity. Right. So now we've proven this this proposition. Question is, have we gained anything by doing this? How do we describe multipliers? So there is an easy way to describe a multiplier. You take a function from the Pontryagin dual of G tensor with itself to the complex number, which is regular and which is regular in a particular sense, and for any f in the Schwarz algebra of G times G, you set this. So you have just you use the Fourier transform, and then you multiply by phi, and this is going to give you a multiplier in this above sense. Right. So now we've seen that these natural transformations of pairs correspond really to such functions phi from G hat tensor G hat to C. We need, however, a bit more conditions to ensure that the multiplication that our natural transformation is compatible with associativity for the vector spaces. Well, actually, we need two conditions. First one is that it's compatible with tensoring with the unit on the left and on the right. And the second one is really that it's associative. Okay, so these two conditions can be translated at the level of the properties of the map phi, and these are so you have a condition of normalization, which is this one, and the condition of cocycle. This is really what ensures that what you have here is associative. And finally, you have a condition of regularity to make sure that if you start from something which is in the Schwarz algebra, you end up with something which is in the Schwarz algebra too. So, to summarize, right. To summarize our construction, we started with a tame-smooth representation satisfies this, a normalized cocycle from the Pontryagin dual times itself to C, this property, and the outcome is that we are going to define a new algebra by taking actually the same algebra from a topological point of view with this new product. And for modules, it's a bit of the same, except that you take another element of the natural transformation. And so this construction, as I said, is also possible for general locally compact abelian groups. In general, you have to make sense of the Schwarz algebra.
So basically, this is
it's except that there is no cross product involved a priori. Yeah, so it's a twisted cross product without cross product. Yes. Yes. So. All right. So now the case of the group when S1 times dead, we have G hat, which is just the same thing reversed. The cocycle you use is this one. You can check that it satisfies all the required properties. And how do we construct, well, explicit examples? We let G act on a C-star algebra by this, and you've got an action of S1 which is implemented by alpha, an action of Z which is implemented by sigma. You define a Fréchet subalgebra, well, in the usual way, asking that this map from S1 to the C-star algebra is smooth. Then, result number one, we have a smooth tempered representation of our group G on a smooth, so we can apply our theory. We'll then consider the spectral subspaces AN defined in the usual way. So these, and explicitly, if we want to look at the deformed product, what we have is that the deformation of an, the deformation of the product of an and am is just sigma m to the power m, this m of an. Then here what you have is the undeformed multiplication. As a particular case, you consider a system algebra C of T2. The action of G that you take is just this one, and this way you recover the non-commutative torus. Okay, yeah. So an additional element which is kind of surprising is the deformation of the involution. So if we start from a construction a bit like that in general, if you start from a construction with a C-star algebra, okay, here I am. With a C-star algebra, it's natural to ask that the C-star algebra is represented on a Hilbert space, and you expect this kind of thing to happen. And so what we're going to see is what is the interaction between the representation of the original C-star algebra and representation of the deformed algebra at the level of the involution. So what we do is that we assume we start with a C-star algebra A, as before, represented on H, and you assume that this representation is G covariant. So you can introduce the smooth version of the Hilbert space. And it is also a smooth tempered G representation. Then you deform, so what you have here is really a map. So pi is going to be a map from A tensor, this smooth version, to H infinity. And this kind of map we can deform using our natural transformations. So that's what we do, and we deform the representation into pi phi, just like that. And now we can ask, what is, if I consider the deformed representation, what happens, what is the adjoint? Is the adjoint deformed by this deformed representation? And the answer is so here it's what you have here is that we're looking at an action of S1. Okay, so it's yeah, and so yeah, but actually that's the main point in this deformation of the involution. What you have is that you have an involution which is defined and which only depends on the grading of the element A, and doesn't depend on the grading of the element H. Yeah, so that's a phenomenon which we can see on S1. The question is whether this is going to happen for more general groups. And Ralph is arguing that yes. So I have some checks to make before telling that for more general cases. Okay, so now examples of these to see how these functorial deformations can be applied to situations, to concrete situations. You take an involutive Fréchet algebra A with a smooth sigma and a grading AK, so that's essentially the setting in which we've been just before. So you have these spectral spaces AK, and you ask that they all admit frames eta, j, k, that is to say, elements in the bimodule that satisfy this condition. Okay. The existence of such frames ensures that algebraically we are really in the case of non-commutative principal U1 bundles in the sense of the work by Piotr. So that's the first condition. So you see at that point it's essentially algebraic. But now what we are interested in is smooth non-commutative U1 principal bundle. So really something which is analytical in nature. And so we have further restrictions. So we're going to ask that the number of elements in a frame for a given K is independent of the chosen K. And we're also going to ask that we have polynomial growth in these frames. And so the lexicographical order which appears here is just to give a meaning to this polynomial growth. And of course, we're in the Fréchet setting, so we need to do that for all continuous seminorms. So once you have an algebra that satisfies all these conditions, that's what I'm going to call U1 bundles for the rest of the talk. But in the papers, we call them tame, smooth, generalized cross product. Understand? I didn't lose much by calling them U1 bundles instead of just this. Okay, but yeah, just keep in mind that U1 bundles means this. So, of course, if you have a definition, you would like to see examples first and a theorem corresponding to this hypothesis. So an example, you consider a compact smooth manifold X. Okay, you take a Hermitian line bundle and you write P of X for the associated principal U1 bundle, just a continuous function on P. Then you have a C-star algebra with an action of S1, and the identity as action of Z. You are precisely in the setting of our previous slides. So you can consider the smooth version of A, okay, and it forms a U1 bundle in the analytical meaning that I have just defined for a certain explicit family V omega L of frames. Okay. So there is just something somewhat strange in this definition is that you ask that the size of the frame is uniformly bounded. Okay. And so in the commutative example, we see how this comes around. It's really that your frame corresponds to systems of to a trivialization of your line bundle, okay, and a generator of the line bundle on each patch of the trivialization. And so the indexed, that is to say the number of elements in your frame, corresponds just to this trivialization. And then you can also look at the Fréchet structure on the smooth element of the C-star algebra. It's given by these seminorms. Then it's a computation which is not so simple, and I can discuss afterwards, to prove that indeed you have polynomial growth in these bundles. Yeah.
So you say that these are units correspond to algebras.
Yes.
Different line bundles associated to the principal one of P.
Sorry, do you get? Precisely, yes. But if you have since the different line bundles are obtained by tensor product, okay. If you take the generator of the first one and you just tensor it, well, actually you've got to be a bit more careful than that. But yeah, you have to take a larger patch on which you have a generator, tensor the generator, and then restrict by a partition of unity. And this way you really get something like that. So I mean, the short answer, which is not completely correct, is you just tensor the generator of the first line bundle. The precise answer requires that you put a partition of unity into account. Yeah. All right, so that was how we construct examples of these U1 bundles. Now I said a good definition should be the hypothesis of a theorem. Here is the theorem. Given such a U1 bundle, in the previous sense, we have a 6-term exact sequence in periodic cyclic cohomology. So this should remind you of Pimsner-Voiculescu exact sequence. So kind of the same in periodic cyclic cohomology. And actually, this 6-term exact sequence is compatible with the usual Pimsner-Voiculescu exact sequence in K-theory in the sense of this transfer formula. So point 1 is actually a generalization of result by Richard Nest. And point 2, this transfer formula, relies on previous result by Victor Nistor. So well, we'll come back to see how the proof goes for this later on. No, what you need, sorry?
Not necessarily commutative.
No.
Only with this condition.
All these, just these conditions. And then you can be non-commutative. No, actually, that's what the point of applying our techniques to this situation is really to prove how, starting from a commutative construction, just like here, you can get a non-commutative one. So here is the theorem. So now that we know more about these U1 bundles, how could we deform them using our construction? So what I say is that this kind of analytic U1 bundle is invariant under this sort of deformation. That is to say, if you start from a U1 bundle, such U1 bundle, with involution inherited from a G covariant representation. Remember, at some point I discussed the deformation of the involution. And if you take automorphism sigma of A, which has a polynomial bound for all fixed semi-norms, then the deform algebra obtained from our construction, from our deformation construction, is also going to be a U1 bundle in the sense I introduced before. Okay. So the gauge action on the deform algebra is unchanged because it belongs to these morphisms which are preserved. And the point is that if you have a system of frames for the undeformed algebra, you're going to get a system of frames for the deformed algebra. And actually, you can take the same frames, and the fact that the involution is deformed is enough to ensure that, with the new product, the old frames are still frames. And since you take the same, the size of frames remain the same, and the growth condition is going to be preserved since the Frechet structure is preserved. So we can have a very concrete example of such construction in the case of quantum Heisenberg manifolds, where you start from classical Heisenberg manifolds, and you deform them to construct quantum quantum Heisenberg. Right. So we've seen that these U1 bundles were stable under the sort of deformation that I was discussing. I'm going to say more that under some conditions, the periodic cyclic cohomology of the algebra is invariant under the deformation. So the hypothesis I required are first that we have this involution inherited from a G covariant representation. Second, that sigma has polynomial bound for all fixed semi-norm. And so these are just the hypothesis we had here. And an additional requirement is that there is a path starting from identity and going to the automorphism sigma that we want to reach, such that for all A in the algebra, U to sigma U, the inverse of sigma UA is a smooth map. So for any fixed A. Then in these conditions, you have stability of the periodic cyclic cohomology. So steps of the proof, both A and A phi are U1 bundles because of the previous proposition. And so we have these Pimsner-Voiculescu sequence, Pimsner-Voiculescu-like sequences in periodic cyclic cohomology. The gauge invariant subalgebra B, which correspond to A0, the zeroth spectral subspace, is left undeformed. And what we need to do is to prove that this map from periodic cyclic cohomology. Oh, like leave. Yes, there is a is left undeformed. Yeah, yeah.
You are right.
Okay, so what we have to prove is that these maps in the six-term exact sequence are the same in the deformed and undeformed case. And then we're going to conclude using quasi-homomorphism and diffeotopy invariance, which are properties of the periodic cyclic cohomology. So here's the proof. About, sorry? Without with the well, okay, I haven't thought about that. Let's see. No, actually that's not going to work because the very first thing is to construct the six-term exact sequence. But okay, I will see a bit about the proof and discuss how this is going to work. So I start by just giving an idea of how the proof of the six-term exact sequence is working. So you start with a Toeplitz extension of Fréchet algebras. So how it's done, it's essentially you take what you have here is a sort of tensor product, well, subalgebra of tensor product of A with a smooth Toeplitz algebra. Smooth Toeplitz is a well-defined notion introduced in particular by Kuntz. Then, since you have this short exact sequence of Fréchet algebras, you can use excision to construct a six-term exact sequence of periodic cyclic cohomology. Okay. Then we just have to replace this and this one by B. Okay, and so that's what we do. We prove a Morita equivalence between this one and B. So, and then our sequence becomes this. And second part is use a quasi-homomorphism to say that this has the same periodic cyclic cohomology as the B, and then you get your six-term exact sequence. So I'd like to pause for a moment on this point because here you say, okay, it's just a Morita equivalence, and here it's a quasi-homomorphism, but the very meaning of Morita equivalence and well, quasi-homomorphism is clear. Morita equivalence in this setting is not that clear. Actually, it's really at this point that we use the condition that the size of frames is uniformly bounded, because we depend on previous work by Joachim Kuntz, in which he doesn't require this condition precisely, but something akin to that. So the two analytical conditions which are here come from this Morita equivalence business. Yes, if you want to put it in a nice way, it's you have your algebra, your first spectral subspace A1. This is really the module you're interested in, and what you have here is the inductive limit of the different of the iterated tensor product. Okay. This is essentially what C is. Sorry. And that's precisely why I was introducing this, because to prove this, we we need to understand what are the maps here. Okay, and so that's what we do to prove that these maps are invariant. Okay, so six-term exact sequence, Toeplitz extension. Good point is that our construction of Toeplitz extension is very natural, and therefore it belongs to this category of smooth tame representations. Okay, provided A is in these two tame representations. So yeah, so you have the same short exact sequence for deformed algebra. You can give a meaning. You can give a meaning to that. You can give a meaning to that, and the short exact sequence stays the same. And so in the undeformed case, you had this diagram, and we said that we know how to do this. This is a monoidal equivalence. We know how to do this. This is a quasi-homomorphism. And we have, since the deformed algebra is also a U1 bundle, we have the same exact sequence. And so you see, here we really get the sequence. If we, we're just looking at HP of B and HP of A are just vector spaces. So if we prove that this map is the same in the deformed and undeformed case, we are done. And so that's what we are going to do. So we need the notion of quasi-homomorphism to go from TA to the algebra B. Okay, yes, sorry. So yes, we are really interested in these squares. That's what we want to study. To study them, we need a property which is invariance under diffeotopies in periodic cyclic cohomology, and this is better done at the level of morphisms, rather than at the level of just maps in the algebra. And so the way we do it is that we lift the maps of the previous square to these to these. Okay, so the map from C to the Toeplitz algebra is just the inclusion that exists. Here is you also have an inclusion which induces the monoidal equivalence. Here you've got a quasi-homomorphism. So I mean that's a central point. So what is the definition of a quasi-homomorphism? That comes from Kuhn's picture of KK theory, a bit adapted to the setting of these special algebras. So you have two morphisms from A to a certain algebra B hat, which contains B, and you have two conditions that of the compatibility of alpha and alpha bar. And so the way we should think of that is that alpha bar is a sort of difference between alpha and alpha bar. Okay, so when this alpha minus alpha bar has a meaning as homomorphism, this is actually true that HP of the quasi-homomorphism is just same thing as HP of the difference. And this notion is what is going to enable us to conclude, because of the very strong flexibility that's given by this algebra B hat. So because the map induced by this quasi-homomorphism goes from A to B, and you don't see B hat at all. It's so this is providing us an additional degree of freedom. And So coming back to our squares, now that we know what's the meaning of this and what's the meaning of that, we can compose these different morphisms that we know well to define this quasi-homomorphism beta bar. And explicitly, when you do the computation, you find that beta of B is just this distance tensor product, and beta bar of B is this, which makes the frames in coming from our definition of U1 principal bundle appear. So yeah, and this composition, this computation, it works for the deform as well as for the undeformed algebra. The expression which is here is going to be the same, except that the product appearing here are going to be replaced with the deformed product. And so when you do the computation explicitly and you come back, so you make the computation in A5, come back to the undeformed product, you obtain this expression. So this expression is somehow very similar to what you would expect from the Pimsner-Voiculescu exact sequence in the setting of Kunz-Pimsner algebras. Okay, and the Xi-J's are the frames. Now, we want to say that the map defined by this beta bar is invariant. So that's the moment when we use this part, this hypothesis of the theorem. Because then you're going to have so this is going to be a smooth map for any fixed A, and therefore we can extend it to Z of B, which is just infinity functions from 0, 1 to B, with the conditions that fk0 equal to f. So yeah, f1 is equal to 0 for k strictly superior. So yeah, so that's, you see this using this definition of this property that this is a smooth map, you can extend beta and beta bar to maps Z of beta, Z of beta bar from B to ZB tensor K, and then B is defined here. Now, the diffeotopy invariance of periodic cyclic cohomology means that the two extremities, so beta 0 and beta 1, induce the same map in HP. And right, so and by construction, the one obtained for the deform for the undeformed one, so beta 0, beta bar 0, is the same as the one obtained for the deformed algebra. Okay, and they factorize via these different maps. And so we've proven the property. Okay, and so summary. Yeah. Summary, we have seen how to define functorial deformations for G, a locally compact abelian group. We've seen applications to smooth tame generalized cross product, that is these U1 bundles I mentioned. We've seen how we could construct such generalized cross product using the deformation, and how the periodic cyclic cohomology of these U1 bundles is stable under deformation. And this is going to appear someday. Okay, so thank you very much for your attention.
take a free action of U1 on the unital sister algebra, by a theorem you know that there is a strong connection. So, for some non-commutative frame, so you have this algebraic principal bundle, and I was wondering whether you could put some axioms on this U1 sister algebras that exist in the U1 equivalent spectrum tuple that would guarantee that you not only have this algebraic and sister algebraic versions which are equivalent, but that you have a smooth version in your sense, just as you convinced that it exists in the case of a manifold. Can you do it not just for manifold, but also?
Yes, yeah, yeah. Well, I actually haven't thought about how this would fit with a, yeah, I mean, how you could, we know already that that sister algebraic and algebraic setting are kind of are equivalent. The question is it true for, well, the fact is the question asking for the, so where is it? Asking for this uniform bound on the number of elements in the frame is kind of restrictive because somehow the evaluation the number of elements in the frame depending on k, the one that you would expect, and so that's your remark somehow, Walter, that it would be k to the square. Sorry, yes, k to the no, sorry. If for the first one you call it n, it would be n to the power k. That's the one you would expect. So you would expect exponential growth of this. So that's if you go just in the algebraic setting, that's what you would get. However, if you look at yeah. But if you look at quantum spheres, and here I speak under the supervision of Gianni, if you look at the quantum sphere, you have this property of uniform of size. So somehow, I would say that what you really would like to have is that if you have a self-Moita equivalence as bimodule here, okay. If you have a self-Moita equivalence which is smooth, you would like to apply this sort of theory, but unfortunately, I'm not able to prove such result for the moment. Yeah.
Why do you avoid using the term connection?
Sorry?
Why do you avoid using the term connection?
Okay.
And possible extensions beyond you want.
Right. Okay. This, sorry? Ah, yeah. Okay, yeah.
Where quiz comes from is a certain cross model. So this looks like it should be generalizable to this case. But then you also use something like pure difference from stuff which only works in the deviant case. And you think this has a non-deviant generalization.
But so, but you're going to deform the action, aren't you? No? Yeah. Well, I think we need to discuss that afterwards. That's probably the best way to do it. Yes. Yep. Okay. Let me just mention that what I call frame, Piotr calls strong connection, but we're really talking about strong connections. Okay, that's a frame. Okay, so it's yeah. So the question, so strong connections, we're going to define them by the existence of such elements that multiply to 1. And so it's linked to the condition when you have a Hopf-Galois extension. Okay, so in this case, you're going to have something like that. And times.
Just a quick comment on the right. So
Yes.
for one derived connection in a classical setting, you get many listings to a derived connection. That's a huge term. But you can always represent one.
No, I think yes. Yes, yes, it's true. Yes.
Concerning the stability of HP. I mean, there's been a thesis from the student by Nigel Dixon about stability of HP for, I think, deformations of this type and smooth deformation of this type. Is there any relation?
Well, the question is, what do you call deformations of this type? Because the idea to use these functorial deformations based on the Schwarz algebra, I think it's very new. So, but it could be it. But it could.
Sort of, Rieffel type deformation.
So.
As far as I remember, I don't remember.
Yeah. Okay. So let me just say that if you look at I mean, this is somewhat different from just Rieffel deformation as defined by Rieffel. Okay, and yeah, well, it could be that in the case at hand, it could be that that both theories applies. Yes.